started?
Since others are not joined, we are planning to wait until 10:10.
Oh, until 10:10. Okay, that's all right. Otherwise, how is the holiday?
For me, it's really rather challenging,
Hmm.
juggling all the things, internship, chores at home, and also trying to teach myself.
Yeah, but I mean, now that you are in the area of computing, that's going to be your life for the rest of your life. It's a journey of so many things to do. But you learn, you adjust slowly by slowly. Don't rush it.
All right.
Mark, how are you? I've not talked to you in a long time.
Yes, good morning, doctor. Morning, doctor. I'm fine. Yes, I'm also busy at home, handling work. Yeah, yeah. There's nothing much going on right now. Yeah.
Wow, it seems I'm going to struggle with network where I am, but it's well. I was saying hi to Mark.
Yes. Good morning, doctor.
Good morning to
I
you. How are you doing?
I'm fine.
Okay.
Yes, I'm
Are
also
you?
here at home. Yeah.
Oh, you're not doing something else.
No, I have personal work that I'm trying to do. Yeah,
Okay.
including this. Yeah.
Okay. That's great.
Right.
Ian, how are things on your side? You seem to be always doing quite a lot.
Things are okay. Just trying to get time to do some stuff, but also work at home keeps me
Mm,
busy. Yeah.
okay, that's good. Did any of you guys apply for the design sprint camp?
Yes, I applied for me.
I applied.
Oh, did you get feedback?
Yes, I got feedback.
Oh, Godwin, I think you even attended the meeting yesterday.
Yes.
Ah, that's good. How about Ian?
Yes, I got feedback, though I didn't reply.
Oh, so will you be continuing with the training or you gave up?
I'm not so sure I'm going to look into it.
Okay, that is fine. Mm.
It's 1 minute to the time. I think we'll have to start without the others. They'll catch up on using. They will have to catch up using the videos. I hope that's okay.
Yeah, I think it's fine.
Yeah. Ian, I think you can kick us off, right? Then I'll come in last.
Okay. I'm going to use my phone to share because my laptop has little power and there's no power here.
That's completely fine.
Ian, I think you are probably not speaking yet because you are muted.
Oh, sorry. I had been explaining. I didn't know I was muted. Right. I hope you can hear me now.
Yep, now we can.
Okay. So last week we covered the NOT gate, and the NOT gate was the first gate we covered, and it's similar to the classical NOT gate. So it flips one state from its, let's say, get state 0 to get state 1. And we said it's an identity matrix. Yeah. So today we are going to cover the Hadaman gate, and this is the first quantum gate. So it creates an equal superposition state of a given computational basis. So this gate contains quantum capability compared to the NOT gate. So it's denoted by capital H, and it turns the state 0 to this. It would be good on a computer, but is this equation. So it turns it from get state 0 to this state. Then when we apply it to 1, we get the same equation, but there's a minus sign. Yeah, so those are just states, but it can also be applied to a superposition. So this is the equation: alpha ket 0 plus beta ket 1. So alpha can represent a complex number, and beta. So it turns them into this state. This looks a bit untidy, but that's how it looks. It's better when it's written. Yes, so there's also the algebraic expression of this gate. So these gates, okay, quantum gates are also unitary matrices. They're represented as unitary matrices. And we dealt last week with the NOT gate, and it's an identity matrix. Even this one is also one of those. So it's denoted by this 1 out of root 2 times into square brackets 1, 1, 1, negative 1. Yes, so if you want to prove what happens to Kate state 0 turning into this equation I showed you up here, this one, we're just going to prove that when you apply it to this state, you get this. So mathematically, this is the first bracket represents the matrix. Then that part Kate 0 is the state. So when you do the math, when you deal with these square brackets first, on the right hand side, we shall get 1 out of root 2 into brackets 1, 1. After multiplying, we remember that math. So what we do, we just separate that 1, 1, and then we get 1, 0 plus 0, 1. So we know that 1, 0 represents the state 0, and 0, 1 represents the state 1. So henceforth, we have proved that applying this matrix on Kate 0 gives us this equation. So that's the Hadaman gate. What can it be used for? So the Hadaman gates and other gates make it possible for computers to take shortcuts that classical computers could not have done, hence solving problems faster. Yeah, if we apply it to the state 0, we get the other equation. Then when we apply it the second time, we get back the original state. So in this diagram, we have two gates put together. So what they're telling us is that when you put these two gates together, you get the quantum wire. Yeah. So the net effect is the same as a quantum wire. This is critical for many algorithms for quantum computing. So that's the end of the Hadaman gate. Last week, the last slide, I forgot to add that also when you apply two NOT gates in one straight path, we get back the same state or the same superposition. So that's it for today, and the next one will be measuring a qubit and its measurement in computational basis. Yes, thank you. If there are some questions, it's okay.
Yeah, Ian, thank you for sharing about the Hadaman gate with us. Personally, I don't have any questions. I think, Mark, would you like to proceed or should I take over? Mark, can you hear us? I wanted to come in last, but okay, let me take over and then perhaps Mark will come in later. Allow me to share my screen. I hope you're all able to see my screen.
Yeah.
Yeah. So today I'll be mostly trying to relate what I've shared about linear algebra from the start up to where we have reached now. Last weekend we looked at solving a system of linear equations using elimination and back substitution. Last time we specifically looked at an equation similar to this one. Yeah, but today I want to bring together all we have been looking at. So some of the things we looked at were basis vectors. Basis vectors. We looked at basis vectors as the first thing we looked at was vectors. We can represent vectors as a column of numbers x, y, or in a two-dimensional system, or x, y, z, and so on. Then we also looked. That's what we looked at vector. Then we looked at we looked at special vectors called basis vectors, and we realized that basis vectors, for example, in a two-coordinate system, were they were the vectors I hat and j hat. They were the vectors I hat and j hat, which were 1, 0, and 0, 1. And these vectors can be used to represent any other vector within this space as a linear combination of these vectors. We also looked at linear combination, of course. Linear combination is simply linear combination. Linear combination of vectors. We looked at linear combination simply multiplying a vector by a scalar and adding them. And linear combinations enable us to represent any vector within a vector within the space as the basis vectors. For example, if we had a vector here, it could be represented as a. I'll not dive too deep into it now. I'm just refreshing us. So if we had any vector here, we could represent it as a linear combination of I hat and j hat. And we realized that if somehow we also looked at linear transformations. And we realized that linear transformations represent kind of moving space. I'll be using a 2D example. A linear combination can mean rotating this space, or simply maybe moving this 2D coordinate system to anywhere, or perhaps rotating it, or even sharing it in some kind of way, basically manipulating space. And every time you move space, the vectors change positions. And let's say if this vector, let's call it our vector v. If this space was transformed and this vector v moved to maybe another position here to v2, and we realize that this vector, if we know the new positions of I hat and j hat, we can simply perform a linear combination on I hat and j hat using the values of the former vector as scalars to get the new position of v2, and realize that the new positions of I hat and j hat can be packaged into what we call a matrix. So a matrix represents any linear, represents a linear, represents a linear transformation. We use matrices to represent transformations. And a matrix is usually the new positions of I hat and j hat. And we can multiply that matrix by any vector to find its new position after the transformation. So that brings us to linear transformations. So that's a brief reminder of basis vectors, linear transformation, matrices, vectors, and linear combinations. Then last week we looked at solving a linear system of equations, and we saw that this system of equations can be represented as a vector matrix multiplication. This equation can be represented in this form, where we have our matrix. Matrix, we get it from the coefficients of all the unknowns. The coefficient of x here is 1, here is 2, and z is 1. 3 is x here is 3, y here is 8, z here is also 1. Since we have no x, we have a 0, and our y here is a 4. Our z also a 1. This matrix that represents the transformation that was applied our x, y, z to get the values 2, to get the new vector 2, 2, 12, and 2. So we looked at how we could represent any system of linear equations as a matrix vector multiplication to get our final vector, which is this. So we can look at this matrix as A, this as our B to get the final vector C. Then we looked at how we can use elimination and back substitution such that we find out which vector B, the transformation of matrix A was applied to get that. That's how all we have looked at so far is related. I don't know if I should go again through the elimination process, but I hope it was clear from the video. Then next week, hopefully, we can look at into depth Gaussian elimination and row echelon in solving linear systems of equations. This week, hopefully I could try to relate everything. And if you had any questions of what you had not understood in all that we have looked at, yeah, that's what I had. So any question in relation to everything we have looked at so far in linear algebra?
Thanks, Godwin. I have no question, but I'll be waiting for Gaussian elimination.
All right.
Great work. Thank you very much.
Thank you. So I think yes, Estin, I've noticed Estin has joined. Estin, thank you for joining us. So Mark or Estin, I believe you can take over.
Good morning once again. Right now I'm going to dive into integral calculus. Yeah, I was supposed to cover it last weekend, but yeah, I hadn't fully prepared, so maybe I can start right now. So integral calculus, so integration is one of like the two operations in calculus that we cover. The other one is differentiation. So differentiation focuses on finding the rate of change of a function, while integration is essentially about finding the total accumulated quantity such as area under curve, or let me just say it's in simple terms integration. In simple terms, integration is like the reverse of differentiation. Then we have types of integrals. We have the indefinite integral, which we can term as the antiderivative. Yeah, so it represents the general form of the function, but without bounds, like there is no interval. So after evaluating it or after finding the integral, we normally add a c for a constant, since the derivatives of constants are zero. Then here we have a table showing the common integrals or the basic rules, though there are more than these, but this is just a sample. We have the k constant. For k is a real number, then or let me say the integral is kx plus c. You see that we've added, here it was, let me say it's x to power 0, then here, when we reverse it or when we integrate, it's an x to power 1. Yeah. Then for an x to power n, yeah, okay. We're going to look at the different types of integration or the techniques where we shall see how to come up with some of these expressions. The other type is the definite integral. It represents the area under a curve, but here it's bounded. It has bound, let me say from x being a, and for x equal to a and x equal to b. Then the techniques of integration. Yeah, integration relies on various techniques depending on the form of the integrand. Integration by substitution is one of the techniques, and it's what we're going to look at first. Yeah, so integration by substitution is used when the integral contains a function and its derivative. Yeah, or when we have like an expression whereby expanding it, for example, this one in this example, we figure that if you are to expand to the power 10, it would be lengthy in working out the integral. So we just substitute the in expression x plus 3, substitute with, let me say, u. Yeah, then we rewrite the integrand, but in terms of u. Yeah, then these are the steps that we take. Yeah, so yeah, I think we are familiar with some of these steps. So we see that this expression, when you substitute for x plus 3 into u, this is the expression that we get. Remember, even the bounds in this expression, they're in terms of x. So we also have to switch them in terms of u in order to get the final answer. However, when we are dealing with u substitution in indefinite integrals, those that don't have bound, you have to get the final expression in terms of x. You have to switch it back to x. Yeah. Then that's another example, but here it's more like a composite function. Okay, a compound function or a product of two functions. Seeing a trigonometrical function and an algebraic function. So we substitute for the angle. Then we follow the very same steps, yeah, to get the final expression. Then the other technique is integration by parts. Yeah, so it is used to find the integral of a product of two functions. It is derived from the product rule in differentiation. If you're to integrate the expression of product rule in differentiation, we get this expression of integration by parts. Yeah, and yeah, this is the formula. Yeah, so this u, or we can call it fx, is a function of x, or whatever variable we use in the expression that you're trying to integrate. Then the dv, or g prime of x, is the derivative of the other function or the other part of the integrand. Then the du is the derivative of the u, and then the v is the integral of dv. So the steps of choosing which one to take as the u and the dv is, one of the commonest rules is the Leater rule. Yeah, so the Leater rule is used to choose which function should be used as the u. So whichever comes in this order, whichever function comes first in this order is what we take as the what? As the u. For example, in this function x is equal to, x into cos x. Using the Leater rule, the algebraic function x that we see comes before the t. The t is the trigonometric function, so we take the x to be the u, and then the cos x to be the dv. Then we follow the procedures. This is another example, or the first example under integration by parts. We are seeing a function, okay, or the integrand as 2x times sine x. This is an algebraic function, and then this is a trigonometric function. So according to the Leater rule, the a comes before the t. So we take the a, which is the algebraic function, to be the u, and then this is taken as the dv, which is the same thing in this expression, in this statement, sorry. Yeah, so from integration by parts, yeah, using the other expression above, these are the steps that we follow, yeah, to get the final answer. Then the next technique is use of partial fractions. Partial fractions, we apply it when integrating rational functions. Yeah, or functions where the numerator degree is greater than the denominator degree. Yeah, for example, we say like x over x squared plus 1. There the denominator degree is greater than the numerator degree, so we can apply use of partial fractions. So yeah, this is another example. We see that the greatest degree of x here is 2, and above it's 0. Yeah, because any number to power 0 is 1, so the x term here is 0. So what we do, we divide the fraction. Okay, we factorize the denominator here, and then we divide, or we separate, I don't know which term to use, or split the function of the denominator into, okay, something similar to this expression, where a and b are constants, to find okay, how to represent the numerator. So after simplifying this, or after solving it, we come up with an expression similar to this. Yeah. All right. Okay. After doing this, we have to generate two. How can I say it? We have to up with two equations so that we can get the values of a and b, and then we fit them back into this equation. Realize that it will be much simpler to solve this directly by using partial fractions other than solving this directly using any other method. Yeah, that's another technique. And then we have trigonometric integrals. These are integrals involving powers of sin x or cos x, tan x, etc. or trigonometric functions. For odd powers of sin x, cos x, we use that triangular, is it equation? I think that's what we used to call it, to write the expression. Then for odd powers, we use the double angle identities. Then we have an example here. 3 is an odd power. So we use the triangular expression to represent it. Okay. Just rewrite it in that using the triangular expression, and then for even powers, sorry, we use the double angle identities. Yeah, I'm quite sure the level that you are on, we've used them before. Maybe right now it's more like a recap. Then another technique or rule that we use is trigonometric substitution. It's used for integrals containing expressions that are similar to these three. Yeah, there's a way we use to derive them, but yeah, it could take some good time, but it's not difficult. However, these are the identities that we use, all the substitutions that we use. Normally, these expressions are taken in, I think, denominators. That's why we normally substitute them, though there are some cases whereby we have to substitute them in what? In single expressions, all those that are not rational. Then, yeah, there is the tan substitution, then the sine substitution, and the sec substitution. Yeah, I think that's all that I have for now. I think the following meeting I'll be handling sequences and series. It will be more of an introduction because it's wide. Yeah.
Thank you, Mark. I don't know, do you want to talk more about that area under the curve?
About the area under the curve.
Yes.
All right.
I don't
Area
know.
under
I
the curve.
might, I mean, I don't know. Maybe the rest of the guys are okay with everything. It's a very
Yeah.
important concept, especially in machine learning.
Yes. So
Feel free to add some more light.
for handling area under a curve, first of all, for that it's supposed to be a bounded. Can I say it? The integral is supposed to be bounded. Let me say on the x. Let me say we plot a function on the graph, and then we want to find area between a certain point. Let me say from x is equal to a to x is equal to b. Yeah, get the expression, and then yeah, can I say it? Then I had, sorry, um, there is that's the simplest method. Then there is finding area between when the let me say the function is split. Yeah, let me say when a portion of it is below the x-axis, so it's in the negatives, and then another portion is above. So there we can handle it as two functions. Yeah, whereby let me say the first bit is above the x-axis, yeah. Then let me say it's between, on the x it's between -1 and let me say and between and up to 3, yeah. Then we use that very same function. When I say it okay, it's better when you're explaining this using visual descriptions. And yeah, I had some resources that I'm trying to look for. It was a PDF, I think.
Okay, thank you, Bank. I think
Oh,
given what you're explaining, it would be good for someone to look at what we call loss functions. Uh, Guys, when you
yes.
get time, try to look up for loss functions. You will see what you're trying to explain, the boundaries. Yes, some could be negative, others could be positive on the axis, but they all have different implications when you look at how the graphs are being plotted, especially when you're calculating the loss or when you're calculating what you're calling the accuracy. And they all have different meanings and they have different impacts when you're training models. So I hope people can look them up. Also, I want to add that for the purposes of learning, I know Mark have ever shared with you a paper. I know probably now that we are moving to second year, we'll start looking at some papers. And so some of these papers have different styles of mathematics. Why I'm using the word styles is because someone can choose to represent something in any way that they deem relevant, so long as they are following the standard mathematical approaches. So someone without the basics in now what we are covering now might not be able to interpret what is being proposed or what is being explained in the paper. So it's very, very crucial. So I encourage you guys, if you have questions, you ask. And again, asking a question doesn't mean that the person knows it all. We all don't know it all, but it gives a chance to learn more and expand on what we know. Thank you.
Yeah, thank you, Doctor. I wanted to inquire, is volume is volume also necessary?
Volume is more of a physics concept, more so in there. Applied math. Well, the beauty with what you're trying to do with machine learning is that it can be applied to any area. So, yes, we can cover volume because at one point we might need to build some machine learning models that can be applied in the area of physics. I'm looking at it more in that area because physics is applied. And of course, we also have, we've been talking about quantum computing. And quantum computing is still physics. Um, yeah, so please, volume should be fine.
Right. Thank you so much.
You're welcome. Thank you too.
Good morning, guys.
Hello, Mr. Easton.
Morning. I hope you can hear me.
Yes, we can hear you coughing. Sorry about that.
Yeah. The bad thing is, I had an issue with my computer, so the presentation that I created has an issue. But I've created some small things that I think we can go through.
It's okay. What matters is having something to keep us going. Oh, sorry, Ian, for hijacking you a bit, please.
Let me see. Okay. Yes, I hope you can see right now.
Yes.
Um, well, I wanted to go through, I was passing through natural language processing before he ended the semester, but Sarah told me to look through language models. Yeah, and I think Hanel was looking through the large language models. I won't reach there, so I'm gonna start from the ones that came before. Mm, yeah, lucky unluckily my my presentation got issues, so I have been trying to create something from the few notes that I had taken down and the resources that I got it from. So from what I got, like a natural language, no, no, a language model is specifically a model. We model how the human's brain ability to produce natural language. That's the simple term. Or we can say it's the probability distribution of what of a words or a word sequence. Uh, see? Yes, yeah. As you can see, language models can be used to create, like, can be used, can be enforced. It can help us to create a lot of, make a lot of things. For example, in speech recognition, machine translation, language generation, or text generation. Then uh, I found that there are two types of language models. We have the probabilistic models, sorry, and then the neural network based models. I think today I'm gonna speak mostly of the probabilistic models, and these ones are static. We use they are statistical methods. The probabilistic models are statistical methods, and in one of them, the best one that I looked through was the word n-gram language model. This one is specifically like it helps us to. It's based on the assumption that it's based on the assumption that the probability of a next word in a sequence depends on a fixed number of words that come before it. The what n-gram model, as you hear the n-gram, it means that the n takes the number of words. Or n stands for number of words. So you can have, let's say, there are very many types. There is a unigram for the unigram model in the n-gram model. For the unigram, we specifically say that each word is independent in the sequence of any other word. So the occurrence of each word is given a probability which is independent to any other word in the sequence. But this one is usually based on on a specific document, what I recall. Then we have a binary word, binary. We have a bigram, I think, bigram, where n is 2. So for a bigram, we consider one word exactly after the word we are looking at. So if we get a sentence, unluckily, when I was trying to create the PowerPoint, I kind of stopped there, but I'll try to explain from the few notes I have. So in a bigram, uh, so in a bigram, since we are using, like, it's called 2 because we are looking at the next word, the word we want to, the probability of the word we are looking at, and the word after it. So we are looking at two words, so it's called bigram. Then anyway, you can just add like a trigram. That means you are basing on 2, words, and n-gram, that means you're basing on n-gram, n words. Then there were, I think, there was a lot of mathematics. There are a lot of mathematics, and like can't capture it right now. I think next time the next time we come, I'll pass through it. A lot of methods where how we estimate the probability of the next word in the sequence using that of the previous words. Mm, I saw a few problems. Yeah, there were a few problems. Like the out of vocabulary words here, like when you're writing a word that is out of English, and the 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 model was taught using English. So you have a word that is not in the vocabulary that was given to the model before. Then mm, I saw something also called a skip RAM language. Here in a skip RAM, instead of using instead of coming from a word exactly after it, we use we skip a word in between the we skip a word, like after one word we skip a word. I can't explain it exactly. I think I can't write. I'm sorry. I'm so sorry. I think I'm going to have to after I recover the PowerPoint I created. I'll pass through it very well. And there's also this thing that I had got. Mm, mhm. Yeah, this is it was a YouTube, but I took a screenshot. So it describes what the language model is in short terms. Like since it's a probability distribution of strings, now here, like if you have a word of we have these the four sentences, so you can see that P1 has a higher probability to be found in an English sentence. A quick It has a higher probability than P2. Anyway, than all of them to be in an English sentence, because it makes uh, an English, it is grammatically right. Then P2 has all English words, but the grammar ain't right. Like if you read it, doesn't make sense, but it has all English words. So it's less likely to happen in a sentence like P1, but it is more likely to happen in a sentence like P3, because P3 has uh, two un-English words with only two English words in it. And P4 uh, has P4 has entirely no English words in it. And that's what the entire language model, I think, was about from what I saw and from what I recorded. But I think maybe next time I'll pass through the entire concept as a whole. By Anyway, if I recover my my PPT. So thank you, and I'm really sorry, but thank you very much for your time.
Easton, there is no need to be sorry. Again, what matters is to start and keep going. And I think you've done a great job. As you're explaining, somehow I was a bit smiling, um, especially where you mentioned the mathematics was heavy. That is true. But so before you move into the rest of the models that I used to build large language models, I request that you first understand that n-gram. It's a probabilistic model. Yes, it's based on statistics and probability. Because if you understand that, and that simple mathematics or hard mathematics behind, then you try to implement it using Python, but then the language or the words you should use should be local words. I mean, local languages. So you can use Luganda. If you want a data set, I can share.
Yes.
So you start with that. make sure you understand the n-gram very well. It doesn't matter whether you present again n-gram next week, it's okay. Because everything else that you're going to cover is based on understanding that basic concept. Up to what we have today, everything is based on that. So they just keep saying, oh, you see now we were missing words, then they introduce some other concept. Again, it's still based on statistics, but also the mathematics, or this mathematics we are covering. So look at n-gram, try to understand the mathematics behind, then try to implement it using any language of your choice, but probably
Python.
Python. Yeah?
Yes, sir.
And then try to see how it works. Then it will be from there that you keep building slowly by slowly. Then I would also like to caution the rest of the team. The concepts that you're covering in your respective topics, if at any one point you see your concept coming in when someone else is presenting, please talk about it. Let us know that, oh, actually I covered a topic like this, and I can see now you're actually utilizing it here. Because at the end of the day, we are going to find that we are almost all doing the same thing. But just that right now we are still working in different groups. But at one point, you'll find that what you're covering or the other one is whatever the other one is talking about, you're going to find it all making sense. And you find that actually it's like we're covering one topic. At one point, we'll be talking about language models and training and everything, and all these other concepts we are covering will be in there. So don't worry, feel free to have all of them learned and shared. And lastly, I think the comment I wanted to make is like, Easton, you are saying that who has similar concepts?
I think Hanen.
Yes.
Yes,
I
he
think you
was,
can always liaise and see what you're talking about and what he's talking about. I thought one is talking about large language models and someone is talking about NLP, no?
and here he was talking about large language models. Yes,
Okay.
me, I was talking about NLP, then I reached on just language models, not large, just language models.
Okay, that's fine. What makes the other ones large is just the content, but that's fine. Yeah, the concepts can be a bit different. So take your direction. It's okay. You guys can always liaise and be like, okay, we'll be covering this week. What are you covering? And then we make it flow. I'll give the last communication later. After, oh, are we all presented?
Yeah, looks like all of us who are here have presented.
Perfect. So, guys, how do you feel about helping me out with C next semester?
C programming?
Yes.
Yeah,
Yeah, I'm on board.
C
I'm on board with
programming.
that.
I think it's okay.
Their concept. Anyway, I have been doing C plus plus. I wanted to try C plus plus, so I think I'm sure I'm not that badly off from the entire concept of C. Yeah, possibly if I have a point, I'll come.
Okay.
Yes, it would be a nice opportunity. Yeah.
Okay.
Yeah, it's also okay with me.
Okay. I think the topics are always there. I will be sharing with you more. But the idea here is not just to duplicate what we studied last or what we studied when we were in first year. The idea is to think innovatively on how we can deliver the content. So it could be that you're looking at linear algebra and you would wish to implement something in C. So the concepts we are studying can actually be implemented in the C language. And so as we share the concepts with the students, then we give examples in that line. So you have to look at what you know and what you're trying to study, and then see how those concepts can be applied in C. Because once you implement them in C, then you can implement them in any other language. So basically, that's the idea. The idea is not just to say, okay, we are just going to teach C and talk about it the way things are. No, I don't subscribe to static things. I subscribe to innovativeness and finding better ways of delivering content. So feel free to roam around and think whichever topic in C that you feel okay with, look at it. And if you want to implement something in your line, even if they are language models, please explore, even if it's linear, explore and see how you can implement some of those concepts in C. It's going to be exciting, but it will also help build your confidence in most of these skills. The rest of the way we will operate in terms of the timings, who comes in when, which groups, because I think I will only be teaching computer science and software. I might not be teaching IT this time. And also, if someone else is interested in mobile, I think I'll be teaching mobile applications. You could still join and we see how that can also be explored. It might be a heavy load for you next semester, but I'm sure you guys can handle. You will be fine. Okay, yes, Godwin wanted to say something.
Yes, I wanted to say for the mobile bit, I think I'll be interested.
Okay,
Yes, trying
great.
yeah, this holiday I'm trying to build a kind of distributed mobile application.
Mm.
Yeah, that uses Bluetooth, and it's like the idea is in halls in halls there's a challenge whereby students want to sell a few items, but they're not getting the market. They, they their market is fellow students. So I want to bridge the gap between them and their market by making a kind of mobile app that utilizes if all students have it, that utilizes Bluetooth and Wi-Fi to advertise the apps to advertise products one students have that they'll want to sell with the rest of the whole people. That's what I'm going
Okay,
to work on.
okay, let's talk about it at certain point. Sounds like a
Okay.
good idea. Mm. All right, Ian, back to you. Me, I'm done.
Okay, thank you, Doctor, for being with us and sharing with us. I think we shall look out for the points that you have noted, like the loss functions and coordinating with other people who have similar ideas. Yeah, I think we can end for here. Doctor, thank you for being with us. Yeah, that's what I have to say.
You're welcome. Have a great weekend.
Have a great weekend too.
Thank you, sir.
Thank you.